Thanks, Danielle and Silvia, for the nice invitation. And well, as after a long day, everybody must be, of course, tired from seeing lots of interesting talks. So, as promised in the abstract, I'll try to keep this very proof-free. I'll try to give a very a talk concentrated much more on, let's say, on open problems and what is new, what is not new, what is open in the area rather than the techniques. I'll comment, of course, every now and again on the techniques, but the focus would not be that. So right. So let's start with the basics, right? So the top of the screen, you can see, well, there's we're going to have three parts. So first is introduction. I'm going to talk about the classical results. Then I'm going to move on to more recent developments. And these involve results in more purely harmonic analysis side and more PDE related sides. And then I'm going to try to connect both worlds with some results that are coming out just now. And yeah, try to leave out a couple of interesting conjectures and open problems for everybody. But well, let's start with the beginning. So pick a Schwarz function and two arbitrary points x0 and psi0 in the real line. What you have is, if you compute the L2 norm of f squared, I can compute it quite simply by this first line. You just introduce this modulation, right? And well, you can also make, of course, in the second line, this artificial derivative of x minus x0 factor. It's completely harmless. And if f is smooth enough, and already we're supposing that f is in the Schwarz class, we can integrate this by parts. Right, so we come up with the third line. And finally, you expand out what the integration by parts gives. And you use a Cauchy-Schwarz inequality, you get the fourth line, which is an inequality. And well, the interesting thing about it is that you can use the Planck-Charel theorem on this first integral on the right-hand side of the fourth line. And if you use Planck-Charel in that, what you get is exactly the following. So you get the Heisenberg starting principle. And of course, you need to approximate. This only holds, this calculation that I did only holds for Schwarz functions. But if you approximate it in a suitable way, in a suitable sense, the following holds. If you have the L2 norm of f squared, you can bound it by 4 times pi times this weighted integral of f hat with this kind of power-like weight, x minus x naught squared. And the same thing with f, but with x minus x naught instead, where x naught and psi naught are arbitrary. And the interesting part is that here one can characterize equality in this inequality. It's just more of a curiosity rather than anything that is going to be vital for us. But the equality in this inequality happens if and only if f is a Gaussian. And this already gives a very interesting corollary. Well, we're going to see that it's not super strong soon, but it's very interesting nonetheless. That if f is concentrated in space around a ball centered at x0, a very, very small ball, and f hat is concentrated also in a very small ball around psi0. And if you fix the L2 norm of f to be 1, then this cannot exist. Such a function must be identically 0. But well, this seems quite restrictive, right? So we're assuming that x0, f concentrates a lot in space around x0, and f hat concentrates a lot on the Fourier side, on the frequency around psi0. So what other things can be said? The first thing that can be said is, well, if f and f hat have compact support, but right now we don't know about concentration, what can be said in this case? And well, there is a not so hard answer to that. You use the Paley-Wiener theorem. If f is compactly supported on the real line, f is an L2, then f hat is an entire function, well, of exponential type, but this is not important for us. And in analytic functions, well, if hat is an analytic function, and if hat's compact support, then it has to be identically 0. So this case is trivial. So then right now, well, let's move on to a different question. Let's just suppose, well, if f and f hat don't have compact support anymore, let's suppose that they have only, that their support is still small, but it can somehow be sparse towards infinity. What can be said? And there is a couple of results. So this was first proven by Benedicts, I think, in the 70s, and then Amra and Bétier strengthened his result. So they proved that if you pick out two sets S and sigma that have finite measure, then I can bound the L2 norm squared of f by a constant depending only on S and sigma times an integral of f squared outside S plus the integral of f hat squared outside sigma. So of course, if f vanishes on r minus S and f hat vanishes on r minus sigma, then this inequality gives us that f is identical to 0 also in this case, right? So right now, let's move on. We talk about sets, functions that are concentrated on small sets. What if we move to, well, instead of saying that our functions are 0 very often, let's say that they are decaying very fast. What can be said in that case? So you have the classical Hardy uncertainty principle, right? So if you suppose that f and f hat are both bounded by a Gaussian, f is bounded by a Gaussian of parameter A and f hat by a Gaussian of parameter B, then, well, if the product of these parameters is greater than pi squared, f is 0. If the product of them is equal to pi squared, then f is the Gaussian times a small constant c, which might be 0 as well, but it is a Gaussian anyway. And if the product lies strictly between 0 and pi squared, then there's an infinite dimensional space of functions satisfying that. So for instance, you can construct quite easily, you can see quite easily that a Hermite polynomial times a standard Gaussian where a equals pi satisfies this last condition for a be arbitrarily close to pi squared, but never equal to that. So this already gives a reason why this space is infinite dimensional, but that is just for people that know a little bit more about orthogonal polynomials and these kind of things. But in general, our kind of question, which is rather than a principle we're searching, is that so somehow this guiding light that we're trying to go after, that, well, pick an operator defined as Schwartz class, and suppose that you can extend it to L1 plus L infinity, or in a sufficiently large class. It need not be L1 plus L infinity, but a sufficiently large class. And it takes, well, it takes Schwartz functions to Schwartz functions preferably, and this new class L1 plus L infinity to measurable functions. And so what we're trying to look when we talk about uncertainty principle is, what kind of conditions do we have to put an f and t of f? Well, and these conditions might vary wildly. It might be decay, support, concentration, regularity, well, zeros, oscillation even, so that f is identically 0. What do we have to put in several different cases? And of course, the answer to that is going to change when we change the operator t. And some examples where it's interesting to look at is, well, the example we have looked so far is t of f equals f hat, the Fourier transform. But some other example that we're going to see right now is where t of f depends on a parameter t, and it's an evolution where the initial value, it's a solution to an evolution equation with initial value f. Or for instance, well, we're not going to discuss this into detail, but it could be, for instance, where t of f is the Hilbert transform or something like that. Well, so let's start talking about, so we talked a little bit about the Fourier transform, right? So this first example here at the bottom. So let's talk about the second. So there's a more in the recent note. So these results that I showed to you guys, they have been proved for almost a century, many of them for way over a century. So let's talk about something that has been developed in the last 10, 15 years, right? So first thing is that, well, let's look at a very naive question. So take the free Schrodinger equation, I dt u equal Laplace u, and to take it these as an evolution, well, where Laplace is just the second derivative of u. Take it just in the real line. Then, well, we have this explicit formula for u of x and t, which is in terms of a Fourier transform of u naught. Well, but then we know that, well, if we know that a function, which is in this case is u naught times e to the I x squared over 4t, decays a lot, and its Fourier transform decays a lot, then by Hardy's uncertainty principle, it should be 0. So that's exactly what it's written there. So if u naught times e to the ax squared is an L infinity, and u at time t times e to the bx squared is also an L infinity, then Hardy's uncertainty principle already for, well, and this condition on a and b is just matching the numerology, then u is identically 0. And, well, of course, this raises the question, what can be done in the case of a nonlinear Schrodinger equation, right? Or even if the solution satisfies the equation with the potential. And, well, there's this very nice theory developed by Scariassa, Koenig, Pons, and Vega, and a series of papers that I think from between 2005 and 2011, something like that, maybe 2012 or something like that, where they have systematically studied the problem of, well, if u is a solution to the following IVP, so it's a linear Schrodinger equation with a potential. Suppose that the potential is bounded and that that V satisfies this limit condition. It basically says that V is quite well concentrated in space uniformly in time, in a certain sense. Then if the product of the parameters a and b is greater than 1 over 16t squared, we're solving in the intervals 0 and t, and the solution at time 0 and at time t decay right now not in L infinity but in L2 as Gaussians, then u is identically 0. And of course, for the case where AB equals 1 over 16t squared, they have a counterexample as well of a potential satisfying, I think, the same condition in the theorem where the solution is not identically 0. But well, their main motivation to do that was to study uniqueness for the Schrodinger equation, right? So if you take this sort of nonlinear Schrodinger equation, I dt w equals Laplace w plus f of w bar, and f is a smooth function, then the difference is going to satisfy this Schrodinger equation with potential, where the potential satisfies exactly what we want, as long as f is smooth enough. So this is a direct corollary of their results, that if u and v are as before, and at time 0, the difference between the solution lies in L2 of a Gaussian, and at time 1, the same thing holds, and the parameter is large enough, so the product of the parameters is large enough, then the solutions are equal. And just a small word on the proof by Scariassa, Koenig, Pons, and Vega is that, well, the main key idea is that they prove some new log convexity properties of solutions to the Schrodinger equation, and in particular in the free case, they have this very nice inequality here, where they bound the basically how much of a Gaussian decay the solution has in a time t in between 0 and 1 by a log convex combination of the Gaussian decay at time 0 and time 1. And they have the sharp, let's say the sharp kind of decay in between, It's this e to the rx squared over 4 times 1 plus r squared t squared, where r is a solution to this equation here. And of course, if you take a look, if mu is greater than 1 over 8, then this equation here that solves r has actually, that defines r has actually no roots, which is a contradiction if we suppose u is not identically 0. So this, what does this mean in their inequality? That you can actually improve this inequality infinitely often and still get as much Gaussian decay as you want, and the right-hand side is going to be uniformly bounded. So the function has to be identically 0. Right, so we talked a bit about this recent development in the PDE side. So as promised, let's talk a bit about the recent development on the more harmonic analysis side. Well, instead of decay, right now we look at zeros as we were looking in the beginning. Then, well, as I said before, there's this Amrhein-Bettier theorem that says that if f vanishes on a cofinite set and f hat also does, and f is in L2, then f is identically 0. So let's construct a counterexample showing that that's not always very important, right? So if you pick out A and B to be two sets where each are very large, just r minus a small dilation of the integers. And well, just pick a function h, two functions h and g supported on a small interval minus delta over 2 delta over 2, and define f to be this sum here. F of x is the sum of gx minus n h hat of n. Well, you can check first that f is non-zero. You just drawing the picture, you just convince yourself, and just the computation is not hard, and it's supported outside A. So it's supported on this very thin thickening of the integers. And if you take Fourier transforms, what you get is exactly that the Fourier transform of f is the Fourier transform of g, which decays, right? Because g is a smooth function compactly supported, and times a periodic function, hp. And this hp is again supported on the same set A. So what this said is that maybe the size of the sets does not matter for this problem, but rather how much they concentrate. So how much the annihilating sets of the function concentrate on infinity. And the first major breakthrough in this area was this interpolation formula by Danilo Radchenko and Marina Biazovska. And well, they proved that you can basically interpolate any function as long as it's regular enough. They don't even need Schwartz and even. They need even, but a little bit regular, not so much. They don't need Schwartz. They can interpolate them as long as you have their values on root n and the values of the Fourier transform at root n. And this interpolation formula converges absolutely, and these functions a n are independent of the f you're picking. And in particular, you get a uniqueness result from that, right? So if f vanishes at root n and f hat vanishes at root n, f is even in Schwartz, then f is identically 0. This result was recently extended to higher dimensions by Martin Stoller in the past year. Right, but one might wonder, so here we have this result for root n on both sides. So it's a very rigid interpolation formula, and you might think, well, it's an interpolation formula. So, and these functions a n, I'm not showing their formulas to you, but they're quite explicit. So, well, one might think that it's plausible that root n has a special property, but for this uniqueness property, maybe they're not so special. And the first result was by myself and Matheus Souza in 2019. We proved that if a function vanishes on certain powers of integers n to the alpha, and f hat vanishes on n to the beta, and alpha and beta, they satisfy this weird conditions. Basically, well, alpha and beta between 0 and 1, and alpha plus beta less than 1 is just a triangle, right? And there's this last weird condition that is a technical condition of our proof, then f is identically 0. But this result, although from 2019, turns out to be already outdated. So there's this very recent result by Kulikov, Nazarov, and Sordin, who proved actually the whole triangle. So this thing in the result I just stated with Mateus, it's a region from this lower triangle, right? They proved in the full lower triangle that if f vanishes at something lambda n that behaves like n to the alpha, which is encompassed in this first condition, and f hat vanishes at gamma n, which behaves like n to the beta, encompassed in the second condition, and f hat are just in H1, then f is identically 0. And they obtained some other interpolation formula, not as strong as the Radchenko-Vyazovska interpolation formulae, but still they obtained something. And right, so the last thing in the analysis side that I'd like to say is that, well, if this result, if you take a look at these conditions on lambda n and gamma n, they do not encompass the case of the Radchenko-Vyazovska interpolation formula, where you have root n on both sides. So in the case where it's asymptotic to root n, it's also not encompassed, and it's a result of myself and Matheus Souza again in 2020, where if you take sup of epsilon n, and here, I'm sorry, there is a typo, and you multiply it by 1 plus n to the 5/4, not minus 5/4, and if this supremum is sufficiently small, then you can interpolate still from a perturbation of root n. So from root n plus epsilon n in both space and frequency. And this also converges absolutely. The functions theta n and eta n are not so nice as the an, but still there is some interpolation formula and you have some uniqueness results. And recently, it's a very recent result from I think 3 months ago or so, me and Martin Stoller have been able to mix up the techniques from these papers with Mateus and from Martin's paper for higher dimensions, and we actually proved that if you perturb the higher dimensional sphere, well, right now the perturbation has to be extremely small. You have to have sigma n vanish, well, decaying like n to the minus the big constant times n. Still, but you can perturb and prove uniqueness from these perturbed spheres. And actually, I'm oversimplifying here because you don't even need spheres. It can be a very, it can be a surface lying nearby a sphere. And these results, well, the first conjecture that I have to show you is that, well, in both of these results, we have this condition of the sup of sigma n and the sup of epsilon n. So the conjecture is, well, you should remove these decay conditions on these things. So in dimension 1, you should be able to put, sup of epsilon n, an absolute value being sufficiently small, then you should be able to interpolate. And in higher dimensions, if you take sup of sigma n sufficiently small, then you should still have uniqueness. But although this is, well, the proof of both of these results with Mateus and with Martin they rely very heavily on functional analysis techniques, and especially on the perturbation of the identity argument. And maybe something else is needed there, but we're not quite sure what so far. Anyway, so right now for the final part, final couple of minutes, I have seen kind of two disconnected worlds, right? So where we had PDEs and Fourier analysis kind of on different sides when we're talking about uncertainty principles. Then there's a natural question, which is, well, what can we deduce from uniqueness of for example, from a Schrödinger equation, if we have information where it vanishes at time 0 and time 1? So, for instance, if you have the free Schrödinger equation, as I previously mentioned, then it's actually not too hard. You can just, well, you just identify with the Fourier transform, and many results actually that I mentioned. So the Radchenko-Vyazovska my result with Mateus, this recent machinery from Kulikov, Nazarov, and Sodin, they can all be translated to this context. But if you add a nonlinear term or even a potential, this translation seems to fail. And it doesn't only seem, I mean, I think, in my opinion, just completely breaks down and something else is needed. So I'd like to just state this result, which is still in preparation, and it's a collaboration with Christoph Kiele, another fellow postdoc in Zurich. He's at the ITS, as far as I know, but also it's a member institute of the ETH. And we have been able to prove a very modest result, but still something that, well, if you take U a solution of the Schrödinger equation, but it's very important that the nonlinearity has this kind of even power type. That is, that it possesses some sort of analyticity. And you suppose that at time 0, my initial data vanishes at spheres of radii log to the beta, and at time 1 the same thing holds, where beta is for any n, and where beta is a fixed parameter between 0 and 1. Then there is a constant k naught depending only on alpha and on the dimension, so that if u naught is sufficiently regular in the sense that, well, it is in a high enough Sobolev space and has a lot of decay, then u is identically 0. And basically, just a couple words on the proof of that, just not to go too much, to extend myself too much further. Basically, what we do is, well, we prove that if u naught, we use this very classical fact that if u naught is regular enough, you can produce more regularity through the Schrödinger equation, through this nonlinear Schrödinger equation, right? So if u naught is regular enough, then u at times 1 is regular enough, and actually you can produce more regularity just by this decay. And you can actually prove that you can bootstrap and show that u naught is going to be actually it's going to decay quite a bit and have a lot of regularity, a lot more than you started with, and use this condition on vanishing to prove that u naught has to have exponential decay together with u at time 1. And there is then you use somehow, well, if at time 0 and at time 1 you have exponential decay, you can somewhat interpolate, right? So in the middle you can have exponential decay as well, but it's a classic by now classic fact proven by Koenig, Pons, and Vega. And you use, and then the last sort of ingredient in the proof is that, well, if you have exponential decay in initial data of this equation, then you can extend the solution analytically for a small time after. So if it's extended analytically and use some sort of result on how zeros of analytic functions concentrate, then you're done. But, well, this is still, like, due to the powers of logs that we have, we don't even manage to get to the full log to the 1th power for technical reasons. It seems that a similar idea is needed to get further than that. And I'm not even sure whether it's able with current methods to get to this to powers of integers in terms of uniqueness for this problem. And the nonlinearity actually plays against us quite a bit. It's not only the strategy of regarding the nonlinearity as a perturbation is it's very troublesome in this case, and the argument with Mateus, it cannot be used from our first paper. On the other hand, well, if you take a look at solutions to this nonlinear scalar field equation delta u minus u plus this nonlinear term equals 0, and if they vanish at some powers which are, again, it's this very densely accumulating powers of log, then these solutions have to be identically zero, and this follows directly from this result, right? So just construct a ground state for this Schrodinger equation, and you're going to have this result for free. But then these observations actually raise many questions, and I'd like to finish and leave you guys with these questions. So what can be said about uniqueness for these elliptic equations, delta U plus VU, or the nonlinear scalar field equation, even if they vanish at spheres of radii n to the alpha instead of log? So maybe in these elliptic equations, things can get better. Can we prove better things for better vanishing results for the elliptic equation? What about other evolution equations like KdV or, I don't know, the higher dimensional models or something like that? What can be said in that context? So there's many nice possibilities, many nice directions, and well, just hope that maybe someone gets as excited about these problems as I am. And if anybody's interested in these things, please let me know. I'm more than happy to talk. Thank you very much.